Day 3. This is the last of it. We'll hit some stuff on density and percent error, both of which are super easy calculations. I think probably a lot of you guys already know how to do density. Yes or no? Yeah? Okay, that's what I figured. All right. So which one would feel heavier? Well, it depends on the volume of that. You know, density has to do with the mass per unit of volume. So, you know, you always ask that question, what weighs more, a pound of feathers or a pound of rocks? Well, they weigh the same. Volume is going to be totally different, though. The ratio that compares mass of an object to its volume is density. I say my dog Minnie, the half Chihuahua, half wiener dog. And she's small. She's really heavy in that little volume. Girlfriend is super dense, very dense. Her vet calls it overweight. I don't, because she's comfortable with her weight at her age. So she's 10. And so she's like, you know what? I am what I am now. So she's okay with it. But she's just very dense because she's got a lot of mass in that little bitty volume. Okay? It's an intensive physical property. Oh my God, what is an intensive physical property? All right, so physical properties, and I'm not sure at what point it comes in here. Physical properties will either be intensive or extensive. A lot of these things you already know, you've heard before. Intensive and extensive properties are new for you. An intensive physical property is a property that doesn't change no matter how much you have. Sounds kind of generic. Doesn't change no matter how much you have. Density doesn't change no matter how much there is. So let's say the density of water, because that's in my brain right now. Water, 1 gram per milliliter. Okay, that's the density of water. It doesn't matter if you have a thimble full of water or if you have a pond full of water. Water's density always will be 1 gram per milliliter. It's an intensive property. It's not going to change no matter how much you have. Let's see. I can use real people names. Remember my children. Andrea. Andrea's shirt is brown. So if I cut her shirt into 30 pieces, what color is it going to be? Brown. It's an intensive property. It doesn't matter whether the piece is this big or whether it's the entire shirt. It stays the same no matter what. Extensive properties change depending on how much you have. So, mass. Okay, if I step on the bathroom scale, I have a certain mass. And then if I pick up my granddaughter and I hold her and step on the scale, my mass is different. It's because it depends on how much you have, how much there is. Volume, massive volume. Volume. Okay, so I got my water bottle today, and I filled it up. I finally remembered. I'm supposed to be drinking way more water than I am. So I fill up my water bottle. I don't know how much this is. Guys, it's really a lot. I feel like it's probably like maybe close to 2 liters. No, close to 1 liter, I mean. Anyway, yeah, probably close to 1 liter. So when I drink half of it, will I still have 1 liter? No. No. Volume is an extensive property. It depends on how much I have. Density's not. Density's intensive. No matter how much I have, it's never going to change. Okay, so that's what an intensive versus an extensive property is. The formula for density is mass divided by volume. Oh, sorry, I'm going to do it one more time and then I'll pull it down. When I taught my kids at Westfield, I was teaching freshmen anyway, so it was kind of hard for them to get very simple things like this. So I would tell them how much I love density. Okay, so it's mass over volume. It kind of helps to remember it. Although I will give you the density formula if you ever have to teach math or science, you have something cute to teach them with. Okay, so you just tell them you love density. And the M and the V. All right. If substances do not mix, the less dense substance will float. if we're looking at these four, this is a really pretty density column. Given the densities of these four liquids, I don't even know what they are. So one's 0.69 grams per milliliter, 1.26, 1, and 0.82. What would be the density of substance A in this graduated cylinder? Which one of these would be A? Yeah. Yeah, the 0.69. Whatever's the least dense will float. Most dense will sink. So what's the density of D then? Which one would it be? 1.26. Right. So they would set up in this column. I told you I wasn't going to raise it again. I lied. Based on their densities. The least dense would be on top. Then we go 0.82, then 1.00, and 1.26. Okay, least dense to most dense. Pretty simple. If an object with a density of 0.95 is dropped into the column, so I have a little object, I don't know, a little piece of rubbery, whatever, it's a marble, something, and I drop it in here. Where's it going to go? Yep, sure will. It's actually kind of cool how it'll work. It'll fit, it'll settle right about there. Okay, it's pretty neat. You can actually do that. Kind of I should probably just leave it up. Okay, this is a tricky one. Go ahead and calculate the density. A block of wood measures 3.2 centimeters by 4.5 by 6.1. That's the volume of a regularly shaped object. Placed on a scale, it weighs 29 grams. See if you can figure out the density, remembering that density is mass divided by volume. That's a big number. Okay. So we use a couple of skills here. You probably got that. How many sig figs can this number have? 2. Perfect. Because your final answer, not the numbers in between, okay, not these numbers. Your final answer has to be rounded to whichever one of these numbers in your problem has the least sig figs. So they all have 2 sig figs. So my final answer has to be rounded to 2. Important to note, do not round until you get to your final answer. Okay? Because it'll really mess up your calculation if you do. So don't round until you get to your final answer. But once I get to my final answer, I can have 2 sig figs. There they are. 1, 2. The 0 is the only number that I can look at to round. Okay? 0 doesn't do anything to that. So my final answer is 0.33 grams per cubic centimeter. Question. If the block was cut in half, what would be the density of the 2 new blocks? Yes, 0.33. Density's not going to change no matter how much you have. I could cut it into 12 little blocks. It could look like a little Jenga game. They'd all have the same density. Okay, that wouldn't change no matter what. That's an intensive property. Okay, so marble weighs 45 grams. When placed in a graduated cylinder that had a volume of 29 milliliters in it, the water level raised to 44 milliliters. So I start out with 29 milliliters. I drop my little object in, and the water level rises. Before you do it, tell me what this is called, what this way to measure volume is. Yeah. Water displacement. Yeah, water displacement. So we use water displacement to find the density of this unusually shaped object. So the mass is going to be the same. So I'm looking for density. Mass is 45 grams. And volume is going to be the final volume here minus this initial volume. So 44 minus 29 is, I really should be able to figure that out this early in the morning, but I can't. Let's see. So what is it? 15. Good, 15. That's what I thought it was. 15 milliliters. So density is mass divided by volume. So 45 divided by 15 gives me my density. How many sig figs can I have in my final answer? 2. So that's not 2. What do I do? Yep, do a 0.0. There you go. That's how to do it. Any questions about that one? Easy stuff. Easy stuff. We're not through the hard stuff yet. Not sure we will this year. A little tricky sometimes. It's pretty cut and dry. Pretty simple. Okay. So let's try to rearrange the formula. So I know my formula is density equals mass divided by volume. So if I'm going to solve for mass, here, let me do it this way. The density equals mass divided by volume. Okay, if I want mass by itself, I need to get it by itself. So I'm going to multiply both sides by volume. That'll get mass by itself. So in order to solve for mass, it's going to be density times volume. And if I'm going to solve for volume, density equals mass over volume, well, that's in the denominator. That's the problem. So I'm going to multiply both sides by V again. Okay, so V's over here. Now I need to divide by density. So divide that by density. Volume is going to be mass over density. Just rearranging. And the trick that all math teachers hate, and I'll probably get in trouble for telling you, make a triangle. Whatever's on the left of the formula goes on the left. What's on the left of that formula? Like physically, what is on the left? Density. So I put density over here because that's the furthest left. What's on top of the formula? Mass. And the only other spot is that one right there. So if I want to solve for mass, I cover up whatever I'm trying to do. And I do the operations left. Cover up mass, density times volume. Cover up volume, mass divided by density. Mass over density. Density, mass divided by volume. Okay, so you can actually use that for any 3-variable equation. I'm pretty sure if Mr. Fox sees you doing that in physics next year, he will throw something at you. So don't, make sure you hide it. If you're going to use it in his class, make sure you hide it. And actually, you're going to be begging for a 3-variable formula next year. Okay, percent error. Going to keep going on. Percent error is a useful tool when determining the precision of your calculation. How'd I do? Did I get the number I was supposed to get? If not, how bad was my number? Okay, so the formula is for percent error is theoretical value, and theoretical values is a textbook value. Okay, that would be your given. That would be something that you would have to be given, something you get out of textbook. Theoretical value minus experimental value. Your experimental value is what you get back at the lab table. You know, I can tell you that water's density is 1 gram per milliliter, but if you go back there and you start making measurements, you may not get exactly 1.00 grams per milliliter. That could happen. And then you're going to divide that whole thing by theoretical value again. Okay? These little bars on either side, what does that mean? Absolute value. Right. So when you get negatives, ignore it. It's the positive. And then make sure you multiply by 100 to get it into percent, unless your brain works, you know, you're like, oh, 0.95, 95%. I got that. Okay, unless you're good like that. Okay, so percent error. The density of lead is 13.6 grams per cubic centimeter. The measured and calculated value is 12.9 grams per cubic centimeter. What's the percent error? So this one right here, this number right here, is going to be my theoretical value. And this number right here is going to be my experimental value. The formula for percent error is going to be theoretical minus experimental over theoretical times 100. Plug and chug numbers. Super simple to do. 13.6 minus 12.9 divided by 13.6 times 100. Okay, I'm going to put equal sign over here. 5.147058824. Okay. I'm going to do 3 sig figs. Okay, because that's got 3 and that's got 3. There's 1, 2, 3. The 7 rounds that number up. So my final answer is 5.15% error. That's pretty good. You probably get an A on that one. Okay. Any questions about percent error? Y'all got absolute value, right? Not hard.
You just do the top and then if you do the top and then times by 100.
Say it louder.
You just subtract theoretical from experimental and then you times that by 100.
No, you divide again. You divide by theoretical. Theoretical goes in 2 places. So your given value, your theoretical value, your textbook value, minus what you get in the lab, divided by your textbook value, times 100. So all that junk times 100. Yeah. See, this unit was really small. It's really short. So why don't you take out your homework packet? Let me see if I can help you do some of it. It's pages 7 through 10, but don't panic. It sounds like a lot, but it's not. So let me get up my document camera here. Yes, ma'am.
Are we going to have to do odds for the dimensional analysis? Or are we fine with just
Evens are okay. If you need more practice, for sure do the odds. But yeah, it was just a lot, and I didn't feel like it was, doesn't need to be punitive. It's not punishment. Although sometimes it might feel like it. I promise you it's not punishment. So let me find my document camera here. Hi. I'm not sure how this is going to work out. Document camera is attached to my webcam. So let's see. Okay, nope, can't do that. Can't have people on camera. So I'll just do them on the board. How about that? If there's anything that you need help with. Density. All right. Pick one. What do you want me to do?
Are we doing all of them?
Yes. Yeah, there's just 6 of them. I'm gonna do some. Oh, and also when today is not a test or a quiz. What you have to do for today is a lab. It's actually a computer generated lab. It's a density of metals lab. It's actually kind of cool. Since we can't yet do labs together, that's what your assignment is going to be. Okay, to do that. It is definitely doable. Okay, it's easy to do and it's kind of fun. Kind of okay. But pick one and I'll do it. Doesn't matter which one. Huh? 5, okay. Need my glasses, I can't see. 28.5 grams of iron shot is added to a graduated cylinder containing 45.50 milliliters of water. The water level rises to 49.10. I need the density of iron. So let's see, density, what I'm looking for. I have a mass of 28.5 grams, and let's see, volume. Let's see, I have 49.10 after I add the lead shot, or iron shot, sorry, and starting was 45.50 milliliters. Oh, here's stick on me. Let's see, 49.10 minus 45.5. Those are kind of strange random numbers too. 45.5, 3.8. Alright, so my volume is 3.6 milliliters. Set up the formula. Density is mass over volume. Plug in my numbers for mass and volume. 28.5 divided by 3.6. See what that is. 28.5. Oh, a lot of numbers. 7.9166. Lots of sixes. How many sig figs can I have in my final answer? I'm looking at my problem. Remember, you can only use the numbers in your problem. No. 3. 3, because 28.5 only has 3. So this final answer gets rounded to 3. There's 3 little sig figs. The fourth number rounds that up. So it's 7.92 grams per milliliter for iron. We got a density problem. Okay, how about some accuracy and precision on the next page? Look at that. I'm not doing the definitions. They're too easy. And I think you can tell the little bullseye things. I worked really hard on that, I want you to know. Trying to put that graphic thingy in there. I'm not good with that stuff. I worked hard. Tell me whether or not those things are accurate or precise. So how about the precision problem at the bottom? Well, I thought that was going to actually be kind of hard. So let's see if we can work on that together. It says a group of students worked in separate teams to measure the length of an object. Here's their data. So it gives all 7 teams. Each team measured the length of an object. So the average length, how do you calculate an average? Add them all and divide by 7. So 2.65. If you guys are faster than me, go ahead. Make sure you shout it out. Plus 80. Okay, I got a number. I got 2.7. Did y'all get 2.7? Okay, good. Okay, so the average 2.7 centimeters. Subtract the highest value from the lowest value. This is your range. So the highest value looks like it was 2.8. So 2.8 minus 2.6. So my range, did you have a question? Yeah. Okay.
Does this subtract the highest value from the lowest?
Should be backwards.
Oh.
I think it's just not worded right. So range was 0.2. Yep, you're right. It should be. Divide this number by 2. By 2. It's like a puzzle. Yeah, this is the approximate plus or minus range from the average. So plus or minus 0.1 centimeters. The precision of the measurement can be shown as the average plus or minus the range. So precision of this measurement was the average plus or minus the range. Yeah, I think that's right. Question? Okay, so this would be like how we determine, sometimes I'll give you, when we can ever do lab, I give you lab, and I know what the number's supposed to be, and I kind of, I let you guys know what the number's supposed to be. And you're like, well, I'm not getting that number. I'm not getting that number. Well, in my mind, I'll kind of do something similar. I'm like, okay, well, plus or minus 5% is fine, or plus or minus 1% is fine. This is the actual way you're supposed to do it if you were going to do it. So I just wanted to give you guys something to, kind of have an idea of precision and accuracy when you're doing stuff like that. So percent error, you have 3 whole questions. I can do one of those if you want me to. If you pick one, I'll do one. Y'all got to work hard. Pick the right one. Pick the hard one. Which one do you want me to do? They're all easy. 2. Okay, thank you. Okay. A student measured the specific heat of water to be 4.29 joules per gram degree C. We'll do thermochemistry later on in the year, and that's the unit. That's all. It's the unit for specific heat. Joules is the unit for energy. All energy. So all energy is measured in joules. And it's like not joules. It's Joules. The literature value of specific heat of water is 4.18 joules per gram degree C. What's the percent error? So my theoretical value is 4.18 joules per gram degree C. My experimental value was that number. So I'm going to do formula, percent error is equal to the absolute value of the theoretical minus the experimental divided by theoretical again times 100. Okay, let's make sure I got it right. 366, right? Yep, 3. So I got a big number, 2, but it's going to end up being 2.63% error. Because it's 2.631, and the 1 doesn't round it up. Question? No? Okay, page 10. Remember about estimated digits? It's going to be the number that's in between the markings, the smallest markings. Let me see if I can actually see these. Okay, looks like that first graduated cylinder. So I see 50, and the markings are in ones. So it goes all the way up to 56. But I have to estimate a digit. 6 is a line. Okay, that's not an estimated digit. One more digit in between those is an estimated digit. Does it look like it's on the line? Okay, so then you give it a 56.0. That's the estimated digit. That's it right there. All right, next one. Yep, those are in ones also. 4.123. Okay, so I have to estimate in between the 3 and the 4 because that's where the meniscus falls. So what do you think? 4.3 what? All right, 4 or 5. Okay, that's the estimated digit. There was uncertainty. Some people said 4, some people said 5. That's the estimated digit. It's estimated. All right, looks like that last one is also in ones. So that looks like 20, 21, 22, 23. What's the estimated digit? What's in between those two lines, between the 3 and the 4? Okay. Okay, as long as you understand that that is the estimated digit. Okay, and if I'm asking you for one, that's how you're going to work it out. Those three balances, I can't see those. I'm going to gloss back. All right, so that first one looks like, okay, my middle rider is 600, so it looks like it's 622.9. Okay, so that's the next digit's going to be my estimated digit. 9 is a line. Okay, that's not an estimate. So what I have to estimate is one past the 9. What do you think? All right, we'll do 1 or 0. Okay, that's the estimated digit. It's different based on the instrument that you're using. All right, let's do that next one. 200. Oh golly, point 1, 2, 3, 4, 5. 200.5, and then I have to estimate in between the 5 and the 6. Okay. I kind of have to go with whichever one y'all say first, because I can't really, it's hard to see. Y'all can see better than I can. Okay, looks like a 4-beam applied balance. 128, I'm just reading the balance, point, oh golly, 19, what? 1, okay. Okay, do you understand how when reading these instruments, what number you're going to have to estimate? Yeah, I hope so. It's going to always be the ending digit. Okay, but it's not a line. It's going to be in between the lines of your smallest, in between the smallest lines. So, all right, page 10 is done. So you just have a few problems to work on, 7, 8, and 9. When you're done with that, go ahead and take the quiz. You can go to one of my computers or do it on your phone. I probably should find out if we're testing Thursday, Wednesday, or Friday.